Okay, guys, so I've got to be honest with you. All up to this point, we've talked about separation that happens inside of a column. And we just kind of gradually have talked about the separation process and how things separate from each other and they eventually come out of the other end of the column. The problem is that proving separation happens on a sheet of paper is a little more difficult than just talking about it. All right? So, separation is very easy to see with my own eyes if it's colored. And we know that it happens. We know separation takes place. The problem is how can we go about proving it on a sheet of paper? What kind of math, what kind of equation, what kind of analysis can I do to prove to you that separation actually takes place? And the problem is that for over 50 years, this has been an issue that we have not been comfortable with. Because how do we explain it? We know that it happens. We can see that it happens. But how can we actually explain the separation process? It's very difficult when you take a few minutes and just think about it. It's one of these things that we take for granted, right? Okay, so imagine yourself in the laboratory and you've got a column in front of you right now, and that column is filled with stationary phase. And that stationary phase allows the separation to take place. And we put a sample into the top. And let's say that that sample has two components in it. We're just going to keep it simple. We've got a red component that's going to be present, and let's say that we've got a blue component that's going to be present. And that sample gets presented into the column, and we know eventually down here at the very bottom, those two colors are going to separate out from us or with us or for us, sorry, and we can collect each one of these colors. So let's say that the blue will come out first. I can collect the blue, and then let's say that the red will come out second, and I can collect that one, and we know that the separation takes place. The question is why? Why does it happen? How? How does it happen? What? What steps are taking place inside of that column to actually allow the chromatogram to separate or the column to provide the separation for us? Well, here's the thing. What we've decided to do is to make something up. That sounds good, doesn't it? We make something up that fits. We make something up that pretty much fits. And then we tell it to you, and we learn chromatography this way, and we never really question it after that point. Okay, so what is this made up story? Well, it's not fully made up, because what they call this is a theoretical, it already sounds wishy-washy. Theoretical? Give me a break. Theoretical plate theory. Okay, so what is this theoretical plate theory saying to us? What should we take away from this theory that's basically kind of made up, but there's some math and justification behind it? Well, theoretical just basically means kind of made up in a way, right? I mean, anytime we talk about theory, we know something's fishy, something smells a little phony. But a theory, using the word theory makes us believe that it's widely accepted and that it's true. And it is widely accepted, and it is kind of true. But the problem is that we've had to make up some parts of the story to make it work out the right way. So what do we work up? Well, we've got to be able to explain the separation process in the column a little easier. So what someone decided to do was say, well, why don't we look at this column and why don't we break it up into segments? And then we can talk about each individual segment instead of the entire column from top to bottom. And they questioned and they said, well, why would you do something like that? And they said, okay, well, watch. In the beginning, I get my red sample and I get my blue sample or my components into that first sliver, the first cut. And then they said in the next step, or in the next piece, what could happen is that the red could maybe travel a little bit further behind, depending on the separation technique, right? So there's my red. And let's say that the blue will go a little bit further down. And then in the next step, let's say that the red is kind of getting held back up a little bit. And then the blue is not in that step at all. And instead it's went down to the sliver that's down below. And then step after step after step after step, we begin to see this separation take place more and more and more. So they basically gave us this theory, or this concept, that instead of looking at the entire column from top to bottom, you need to break this down into tiny little slivers. And if you look at the tiny little slivers, that's what we're going to call the plates. Those are the tiny little individual steps that promote separation. And then when you step back and look at the full picture, you can put all of the plates together and have a streamline motion that begins to take place. Now, when I explain this to people, they get very confused. They don't really understand what I'm talking about. What are you saying? Individual steps, and then you take a look at the overall picture and fluid and motion comes around. The answer is yes. So let me explain to you a little bit about how chromatography relates to Art 101. Okay, so this video has actually paused midway through, and if you're watching this and you get something choppy, then you know what's happened, and I don't really know where I've left off. So I'm just going to kind of quickly recap a little bit on what we've been talking about as far as the column goes to maybe make up for some of that lost time, so this video doesn't have to get re-recorded for the 8th time. And I'm seriously, when I say that, this has taken me 8 attempts to record this video. One of the longest times that I have ever tried to make a video in my life. All right, so just a quick recap. We were talking about the column, we were talking about things separating, and we said that those individual steps are plates. That, I think, was recorded. And then I kind of related the separation to a cartoonist. And I said, if we give a cartoonist either 30 sheets of paper or 100 sheets of paper, which cartoonist could give us a better cartoon? And we said the one with more sheets of paper. And the reason is because they can pick up the small changes a little bit better. And the cartoon would look it would look smoother compared to the one with 30 sheets. So we said plate number was very similar. If we have a column with a high plate number, then the high plate number will be able to pick up the small changes that happen, and those small changes allow us to get better separation. So if you're looking for good separation, choose the columns with high plate numbers. The cartoonists with only 30 pages, well, they're more limited, and their cartoon would be very choppy because they can't really give me a very fluid motion because of that. They're restricted. The same thing happens with a column. If I have a column with a low plate number, the low plate number means less individual steps are taking place. That means a choppy separation is going to begin to happen. And that means in the end, my chromatogram looks a little worse. So what I told you before this video paused is that the plate number, the larger plate number, gives you better separation every single time. Period. Point blank, right? The problem is that time is money. So it takes less time for the cartoonist with 30 sheets to draw the cartoon. The separation's not as good, but this cartoonist will get done with his job quicker. And the cartoonist with 100 sheets that he has to draw, that will take a little bit longer. So if I'm working in a laboratory and I'm looking at time, because time is money, then higher plate number gives me a better separation every time. But it also gives me longer run times almost every single time. And that's something that I have to weigh. That's something that I have to make a decision with to say, is the separation better? Or do I want to put a focus on the time commitment that's required for this chromatograph to be generated? And that's something that your laboratory will kind of tell you what they want and what they prefer. Maybe the separation is okay, and maybe they want to go smaller because they can process samples quicker. But that's something that you don't know till you get to that point. All right. Something else that we need to talk about plates while we're having the discussion is the thickness of the paper. All right. So the thickness of the paper is actually going to be very important. For these cartoonists, if you have very thick pieces of paper, then it's going to be very hard to make the flip book. It's going to be more stagnant. It's going to be more stiff. It doesn't actually flip well at all. And your cartoon could be very choppy because of that. So if you have a very thick plate, then that means that your separation is not going to be good or as good as a thinner plate. If your plates are very thin in height, then this means that you'll probably will have good separation because the pages are thinner. And in a flip book, thin pages work so much better because you're flipping through them one by one, and it's basically allowing you to see a smoother transition from page to page to page. So this is what we call plate height. And plate height is going to be very important for us as well. So not only do we talk about the number of plates, but we also talk about plate height as well. So what we want in chromatography, if we ignore time and pretend like time is not a problem at all, what you want in the world of chromatography is a very high number of plates, and you want a very low, what we call plate height. Low plate heights give you better separation. A large number of plates give you better separation. And these two go hand in hand. So let me draw a diagram and kind of explain. I'm going to do two columns, one to the left and one to the right. The one to the left will have 1, 2, 3, 4 plates. 4 individual pages that the cartoon is drawn on. And the one over to the right will have more pages. Now you can compare and contrast. This column has a very low number of plates. This column has a high number of plates. I can count them. There they are. If I relate that to the height of the column or the plate itself, right, there's the height. I'm going to abbreviate that with an H. Well, the height here is very large. It's a big number. They're tall, right? I'm filling up the same amount of space in each column. This height is going to be a little bit taller because there's only 4 of them. Well, same amount of space here. There's more plates in the same given area. So that means that my height is going to be a little bit smaller. It's not as tall. So this height is going to be very, very low. And that's what I want to see in a good separation with a good column, right? This is going to be more preferred. I get larger number of cartoon pages, I get thinner sheets of paper, and that allows my separation to take place much, much better. Now, there is an equation that we can use that relates all of these things together. And it looks like this. HETP equals L over N. The other version of this is H is equal to L over N, if I want to be lazy about it. HETP stands for height equivalent to a theoretical plate. Height equivalent to a theoretical plate. If I come over to the diagram, here's my H. That is the height equivalent of the plate right there. There's the H. That's what gets used in this equation. Because some people don't want to write HETP every single time, they just convert that over to an H, and it means the same thing. Height equivalent to a theoretical plate. But all the abbreviations just aren't there. The L. The L is the length of the column. So the column length from the top all the way down to the bottom, this is my abbreviation or the value that I would use for L, length of the column. And N is the number of plates that are inside of that column. So basically what this equation is doing, kind of simple, is that it takes the length of the column and it divides by the number of plates that are present. And this gives you the height of each plate that's inside of the column. That's all that it's doing. That's all that the equation's used to calculate. Or if you know two pieces of the puzzle, you can calculate the other one, right? If you know the height and you know the number of plates, you'll be able to calculate the length of the column. If you know the length of the column and the height of the plate, then you'll be able to calculate the total number of columns altogether. But that is one way that we can calculate the height of a theoretical plate. Look at the column. How long is it? Now, how many plates are on the inside? You take the two, you divide them, and you pop out a number, and that number is the height. Okay? So that's where this video is going to stop. And in the next video, we'll pick up from this, and we'll talk about how to calculate N, which is the number of plates, if it's not given to me.